Okay, hello, welcome to my channel. Now in this video, we want to learn how to evaluate limit of functions just by using the L'Hopital's rule, okay? L'Hopital's rule. All right, good. So this tells us that if we are to evaluate the limit of a rational function, we have it to be f of x divided by g of x, okay? Maybe not rational, but just a function is in a fraction form like this. And as x tends to the constant c, okay, maybe by substituting c into the functions, we have 0 over 0 as an output, okay? Or maybe we have infinity over infinity, or minus infinity over minus infinity. These forms here, okay, they are indeterminate forms of limit. So just put it down here, indeterminate. They're indeterminate forms, all right? So when you have this kind of situation, 0 over 0 or infinity over infinity, we can use the L'Hopital's rule, which tells us that the limit that we wanted to evaluate, okay, the limit of f of x over g of x as x tends to 0 is the same thing as the limit as x tends to c here, not 0, right? The limit as x tends to c of the derivative of the numerator, which is this, divided by the derivative of the denominator, okay? So all you just need to do is differentiate the top, differentiate the bottom, and then substitute c again into the functions or into the derivatives and see if you still have an indeterminate form. Now, this rule can be applied more than once. That is to say, you can differentiate the top and bottom more than once, all right? Good. If after differentiating the first time, you substitute c here, and it still gives you a 0 over 0 situation or an infinity over infinity situation, right? So you can apply this rule more than one time. Differentiate the numerator, differentiate the denominator, and then plug in the values. Okay, what we'll be doing here is to test this rule first, all right? We are going to test this rule by, first of all, evaluating this limit without using the L'Hopital's rule, okay? Just by some trigonometric identity or just by some tricks, okay? Maybe multiplication or division, anything, to get the result. And then we are going to compare it with when we evaluate this limit using the L'Hopital's rule, okay? Good. Okay, so let's start by just the normal way. So I'm going to start by multiplying the function at the top and the bottom by 1 over 2x. Or maybe you can say, let's divide the top and bottom by 2x, okay? So I'm going to put this down as the limit as x tends to 0 of the numerator, there is sine 2x, okay? So I divide the numerator by 2x, and I'm also going to do the same thing to the denominator. So we have here x plus tangent of x, and then I divide the denominator by 2x. This is just a way I can figure it out, all right? Just to check out before we use the L'Hopital's rule. Good. And then we are going to see from our basic, or from one of our limiting rules, that when we take the limit of the quotient, okay, it is the quotient of the limit. That is to say, I'm going to put this down as the limit as x tends to 0 of the numerator, okay, divided by the limit of the denominator. So the numerator here is given to be sine 2x divided by 2x, all right? And then we divide that with the limit as x tends to 0 of this denominator. Anyway, I can split these fractions, all right? This is x over 2x. That will just give us 1 over x. Then I add it with tangent x over 2x, okay? That is just tangent of x divided by 2x. Good. Great. Okay. I'm going to use a well-known property that when we take the limit as x tends to 0 of, let me just put it down here for you, the limit as, let's use theta in this case, theta tends to 0 of sine theta over theta, the result here gives us 1, all right? We can prove this using geometry. Good. And also, again, for you to note that the limit of tangent of theta over theta, okay, as theta tends to 0, the result here is still 1. So the result here is still 1. So this is something for you to note. And again, this one also. Okay, so we're going to use those things. And you see that as x tends to 0, 2x here, 2 times 0 will be 0, okay? So as x tends to 0, this angle will also tend to 0. That rule tells us that when theta tends to 0, then sine theta over theta will be 1, okay? So here we're going to have sine 0 over 0, right? A kind of situation. So the rule tells us that we're going to have 1 in the numerator. And again, as x tends to 0, okay, we're going to have, look at this, this is x over 2x. Oh, that is 1 over 2. Okay, it's 1 over 2, right? You know, if you divide this and that, you're going to have 1 over 2. So as x tends to 0, we're going to have 1 over 2. You know, there is no x here. So as x tends to 0, this term will just remain constant, all right? Limit of a constant is a constant. All right, we add it with, well, as x tends to 0, tan x over x, okay, with this part is what we know. It will tend to 1, okay? Good. So we're going to have 1 over 2 times 1. Times 1, which is just 1 over 2 there. So what this tells us is that the result here is going to be 1 divided by 1 over 2 plus 1/2, okay? That is just 1. So the result there is just 1. Just by evaluating it without using L'Hopital's rule, okay? We get 1 as an answer. Good. So to test this, I'm going to have to apply the L'Hopital's rule, okay, on that, and then we will compare the result with the 1 here. So I'm going to write this 1 as a result, so that we will compare it after evaluating this limit using L'Hopital's rule. Okay, let's go ahead and clean this part of the board and use L'Hopital's rule immediately. Okay, and now from the rule, it tells us that the limit of this over that as x tends to c is the limit of the derivative of the numerator divided by the derivative of the denominator. Then we take the limit as x tends to the constant. Good. Okay, so here we have the limit of sine 2x divided by x plus tangent of x as x tends to 0. So let's just apply the L'Hopital's rule real quick. So we want to differentiate the numerator with respect to x and also differentiate the denominator with respect to x. Good. Great. So when we differentiate the numerator, I'm going to put this down, the limit as x tends to 0. Now the derivative of the numerator will be this. Take note, this is sine of a function of x, okay? So we have the function of a function. So I'm going to apply the chain rule. So we start off with the first part, the first function, which we see is the sine, okay? That is the outside function. The derivative of sine of something, okay, with respect to x will be cosine of that thing. So sine of something, the derivative will give us cosine of that thing. And that thing here is 2x, okay? By chain rule, we are going to multiply that with the derivative of the inside, okay? So when you differentiate the outside, put what you had here, and then you multiply it with the derivative of the inside, which is just 2. That is the derivative of 2x. Good. And then we take it with, that is divided by, the derivative of x with respect to x is going to be 1, all right? And then plus, anyway, the derivative of this tangent function, if we differentiate tangent of x with respect to x, we have secant square x, okay? So just put it down for you, secant square x. So this is cosine 2x times 2, okay? This 2 is not multiplied with this angle, rather this 2 is multiplied with the whole function. So I can rewrite the numerator as 2 times cosine x, all right? So I like to put it in that form. Anyway, as x tends to 0, let's do a substitution and see if we are going to have a 0 over 0 situation again. Now, I didn't point this out to you. If you observe from the function, if we were to plug in, as x tends to 0, if you were to plug in 0 here, you will have sine 0, which will be 0 at the top. Then 0 plus tan 0 is 0 again. So we're going to have 0 over 0 situation, all right, which is an indeterminate form, as I've pointed out here. So that is why we are applying the L'Hopital's rule. Good. Okay, so as x tends to 0, you have 2 times 0 there is 0, okay, by substitution. Then we have 2 times cosine of 0 is noted to be 1. That's going to be 2 times cosine 0 is 1, divided by 1 plus, again, secant 0 is 1. So secant squared of 0 will still be 1, right? Because you are squaring 1. So we are doing that by substitution because that function is defined for all real numbers. Good. Okay, that function is defined for all real numbers. Good. Okay. So what we have here is 2 times 1 is just 2, divided by 1 plus 1 is 2 again, and what we enter with it is 1. So the limit of this function, okay, as x tends to 0, by applying the L'Hopital's rule gives us 1, which is the same thing that we had when we just evaluate the limit in a standard way. So that tells us that the L'Hopital's rule works for this function. Anyway, this is a well-known rule. It works for millions of functions, all right? So this is what we'll be doing whenever we have the 0/0 situation or the infinity over infinity indeterminate form. We'll be applying the L'Hopital's rule by differentiating the numerator and then differentiating the denominator and plug the value x is approaching in and see what we have. Okay, great. All right. Let's go far and solve many other complicated examples than this. All right. Thanks for watching. Please subscribe to my channel.